One of the main purposes of finding a sample and computing a statistic like the mean of the sample or the proportion of the sample, is so that we can better understand the population. So we want to know how well a sample statistic will estimate the population. So a confidence interval is something that allows us to interpret how well a statistic is likely to represent a population, and the population parameter, in fact. A confidence interval is an interval where we are a certain % confident, that is called the confidence level, that a true population parameter is within the interval. What this means is that we will find a sample statistic, and then we will evaluate the sample statistic with a confidence level, meaning a % we are confident that our population parameter is within a certain interval. So what I like to look at this is as a normal distribution. Here is my normal distribution, and let's say that we want to find a confidence interval that relates to a population mean. We are going to find an interval. Let's say we want to be 95% confident. That means underneath our normal distribution, we are 95% confident that our population parameter or our population mean is going to be in this interval. Okay. The end tails here are how much we are not confident. Or in other words, the end tails will be our error there. So if that's 95%, then each of these end tails have to be 5% together. So the error would be 0.025 in the area outside of our tails. Okay? We can find a z-score that relates to each of these end tails. This one will be the negative, and that will be the other one will be the positive. All right, so most confidence levels that are used, the ones that are used the most, will have a 90% confidence level. We will have a 95% confidence level, and then we also use often a 99% confidence level. Those are the 3 most used ones. Now, there are different types of confidence intervals that will be constructed depending on 1, what the parameter you are trying to find is, and 2, what information we know about the parameter. So let's take a look at the different types of confidence intervals that involve a population mean. The first type of confidence interval that we can construct is a confidence interval for the population mean when the population standard deviation is known. Now, most times if we don't know the population mean, we are not going to know the population standard deviation. But there may be few cases where this happens, so let's look at this one first because it is actually the easiest one to find. So step 1 says, find the confidence level and then find the area in each of the 2 tails of the normal distribution. So I'm going to show you here part of step 1. That wasn't very well drawn here. Let's say we have a 90% confidence level. They'll have to tell you the confidence level in the problem, and if they don't, just use 95%. So if I have a 90% confidence level, that area corresponds to 0.90. Then that means the area for each of the 2 tails here, so this area and this area right here, need to be 0.1 together, which would be here 0.1 divided by 2, which would be 0.05 in this tail, and 0.05 in this tail. Okay, we call the area alpha over 2, because alpha is the area, the opposite of the confidence level, and we divide it by 2 because there's 2 tails. So that alpha over 2 is equal to 0.05 with a 90%. All right, if we had a 95% confidence level, that wasn't drawn very well either. I'm struggling with those. We have 95% here. So the area in each of the tails, then, this tail and this tail, the total area for both of them is 1 minus 0.95, so 0.05. So the area for each tail then would be 0.025 in that tail on the right tail and 0.025 in the left tail. That means my alpha over 2 is going to be 0.025. Now let's look at the 95% confidence level. Here and here, or 99. So that's 99%. So that means the area for each of my tails here and here would be 1 minus 0.99, which will give us 0.01 divided by 2 is 0.005 and an area of 0.005 here. That means at a 95% confidence level, my alpha over 2, or the area in each of the 2 tails, would be 0.005. So that's the first step, is you need to determine first your confidence level and then the area in the tail of your confidence level. Alright, step 2 is to use the area in the one tail to find the z-score using the z-chart. Now we call that value z alpha over 2 because it's the z-score of that. So whatever that alpha is, we're going to find the z-score that corresponds to it using the chart. So we'll have this chart here, if we can take a look. At a 95% confidence level, our alpha is 0.025. So we will just go and look for the area that gives us 0.025, which will be right there. So that means that, we have the z-score of negative 1.96. So you just find that. Now, if your z-score is directly in between 2 areas, you'll just find the average of those 2 z-scores. Now, the good news is there's because these are the z-scores that are always used, they kind of use the same numbers every time. If we have a confidence level of 90%, then your alpha is 0.05. So that means that your z-score of the alpha over 2 is equal to 1.645. If you have a 95% confidence level, our z-score that we use, so our z alpha over 2, is going to equal, well, we just found that one is 1.96. Now on the chart, it may say negative 1.96, but we'll just use the positive of it because they're symmetric. And then the 99% of our z-score will be 2.575. So those are our 3 most used z-scores. So those are probably good ones just to remember. Step 3 will be to find the margin of error. So the margin of error is equal to z alpha over 2, so that's our z-score, times our standard deviation divided by the square root of n. Okay, this is our population standard deviation on the top here, And on the bottom, that's n, is the sample size, so the square root of the sample size. Okay, the last step in constructing a confidence interval will be to actually construct the interval. So what you're going to do is it will be your sample mean minus the margin of error is less than your population mean is less than your sample mean plus the margin of error. So what you have here is it's just your sample mean plus or minus your margin of error is what gives you the interval that your population mean will fall on in given a specific confidence level. Alright, the last thing to do with these intervals is once you actually construct the interval is to interpret the confidence interval. So to interpret it, what we say is we are 95 or whatever confidence level we have % confident that the interval actually does contain the true value of the population mean. Alright, now that we've talked about constructing a confidence interval when we know the population mean or know the population standard deviation, we need to discuss how to construct a confidence interval when the population standard deviation is not known. Alright, so let's construct the confidence interval when the population standard deviation is unknown, which seems like a more likely instance if you're taking something from a sample, a mean or proportion, and you don't know the population mean. More often than not, you also don't know the population standard deviation. So some important things about this. The z-score normal distribution is how the population is distributed about the mean with the population standard deviation. So when we don't know the population standard deviation, we can't use the z-score normal distribution. So because of that, we're going to use an alternate distribution, and it's called the t-distribution. Okay, and we have to use that because we do not know the population standard deviation. So once again, if you do not know the population standard deviation, we can't use a z-score. We have to use a t-distribution. All right, so the t-distribution helps us describe the distribution when all information about the population is unknown. It's still going to be somewhat normal here. It will look like that. Okay, usually it's a little bit higher, but that's okay. The shape isn't 100%, doesn't have to be 100% perfect. So we'll still have a confidence level that we want to find. We'll have our n that's given to us, the sample size. The only difference is instead of a population standard deviation, we have to have a sample standard deviation. Alright, so first thing you need to do is find the confidence level and then find the area in 1 or 2 tells. And I will just use 95% as an example here. So if my confidence level is 95%, then the area in 1 tell is 0.05. The area in 2 tells would be 0.025. So that's good information to know when you're using the t-distribution, each of those. Now, on the t-distribution, you just need to know one or the other, but if you can relate the two together, then that's really good. Step 2, if you're given a sample size of n, then you want to find the degree of freedom by finding n minus 1. So the degree of freedom is always 1 less than your sample size. That relates to, remember when you were finding the standard deviation of a sample, it would be n times n minus 1. The degree of freedom is why you had to go n minus 1. So here, if we had a sample size of 101, then our degree of freedom is equal to 101 minus 1, which would be 100. So the third step is we're going to use our degree of freedom, which is our n minus 1, and we're going to use our alpha or alpha over 2 to find the t-score of the chart. So let's say that we had a degree of freedom of 100 and our alpha or alpha over 2 was 0.05. We're going to look at the chart and read how to interpret the chart. So here is the t distribution here. So if you look up at the top, we have the area in 1 or 2 tails. So if I have area in 1 tail is 0.025 and the area in 2 tails is 0.5, they relate together, so you don't have to find one or the other. If you know both of them or whatever you want, it works. So let's say that we have the area in 1 tail or 2 tails. 0.05 was our 2 tail here. And then we had our degree of freedom was 100. We have our degree of freedom's 100 and we have our chart going down. You find where the two meet and you have your t-score. That will give you your t-score on this list. So our t-score would be 1.984. So as opposed to the z-score where it's always the same z-score depending on your confidence interval, the unknown standard deviation will give you a t-score which will change based off of the area in the tails and how many data values you have. Now the higher amount of data values you have, the closer your t-score approaches a z-score. The next step is to calculate the margin of error. So we have our margin of error is equal to the t-score that we found times S, which is your sample standard deviation, over the square root of our sample size. So it's the exact same formula as when we know the population standard deviation, except for that the t-score was a z-score before, and our sample standard deviation was a population standard deviation before. So they're the same concepts that get plugged into the formula. So the last step is to construct the interval, which is your sample standard or your sample mean minus the margin of error is less than your population mean is less than your sample mean plus the margin of error, which just means your population mean is in between your sample mean minus the margin of error and plus the margin of error. And that's how you construct it when the population is unknown. Now remember that this means that we are 95% confident that the interval actually does contain the true value of our mean, or whatever percent our confidence level is. It does not mean that 95% of the data value are within our mean. It just means we are 95% confident that our population mean is within the interval.